For a ship to float safely, it is required to be in a state of stable equilibrium. The following media illustrates the factors affecting the equilibrium. When a ship is in unstable equilibrium, it continues to heel when inclined to a small angle of heel by an external force. When the G goes above the M, the ship gets a negative GM as shown. In this case, the ship is unstable. When a ship is in neutral equilibrium, it will tend to remain at that angle when inclined to a small angle of heel by an external force. When the G and M coincide, the values of Gm, Gz, and moment of statical stability are zero. When a ship is in stable equilibrium, it will tend to return to the initial position when it is inclined to a small angle of heel by an external force. When G is below M, the Gm is positive, the Gz is positive, and the ship has a positive moment of statical stability. In other words, a positive righting moment. The moment of statical stability is a product of the displacement and righting lever. From the diagram, Gz is the product of metacentric height and sine angle of heel. By taking precautions to minimize the virtual loss of Gm, you will be able to maintain the stability of the ship. The general precautions to ensure the stability of a ship are: plan stowage in such a way that heavy cargo is stowed in the lower holds. Ensure that the number of slack tanks is kept to a minimum during passage. Keep small tanks slack and the big tanks either full or empty if there are different types of tanks. Subdivision of tanks reduce the free surface by 4 times, and as a result, the GM loss can be minimized. When this GM is a large positive value, the ship is called a stiff ship, whereas when the GM is a small positive value, the ship is called a tender ship. A tender ship has a large angle and a period of roll, while stiff ships have small angles and periods of rolls. When the ship tilts due to external forces such as wind or waves, then the transverse inclination of the ship is called heel. The Km is assumed to be constant only at small angles of heel. The more the ship heels at some angle of heel, the Km increases sufficiently to equal Kg as shown. The angle of heel at which this occurs is called the angle of lull. Normally, at the angle of lull, the ship oscillates about this angle and returns to her angle of lull position. However, even though the ship appears stable at this angle, this condition is dangerous and must be corrected. An unstable ship with an angle of lull could capsize if proper precautions are not taken. Because it is heeled by an external force, it will continue to heel. The ship will not come back to its original position. The steps you have to take to correct angle of lull are: press up all slack tanks and lower weights if possible. Run up salt water in the ballast tank on the low side. After this tank is full, run up its counterpart on the high side. Repeat actions 2 and 3 with other tanks until the ship becomes stable. If you are discharging or jettisoning cargo from the deck, discharge from the high side and make allowance for a shift of the ship's G if you are doing so with the ship's gear. Always calculate the effects before deciding on any action. You can now see the GZ curve drawn for a typical ship. Righting lever GZ at 25 degrees angle of heel is 0.9 meters, 2.95 feet. At the angle of deck edge immersion, the slope of the curve will become less. Maximum riding lever is 1.3 meters, 4.26 feet, at 40 degrees angle of heel. Range of positive stability is 0 to 68 degrees. The angle of heel at which the riding lever, GZ, changes from positive to negative is 68 degrees. The point of intersection between 57.3 degrees angle of heel and tangent to the curve gives the initial metacentric height. GZ curves are used for calculations, from which the riding lever about an assumed CG for any angle of heel at any particular displacement may be obtained by inspection. The curves represent an extensive set of calculations for the naval architect, but you will consider the angles of inclination normally. To get the GZ values, you have to refer to the KN table in the hydrostatic booklet. The designer of a ship must produce information to calculate the GZ. This is done by producing KN values. Refer to the extract from the stability booklet for details. In the diagram, the ship's true riding lever is GZ. Drop a perpendicular from G to meet KN at X. Now, GZ is Kn minus Kx, and Kx is the product of Kg and sine theta. Hence, GZ is Kn minus the product of Kg and sine theta. However, if the ship's center of gravity is at G, the true riding lever would be the GZ value. In practice, the true GZ is always less than the tabulated Kn value. Therefore, a negative correction is applied to the tabulated Kn value to obtain the true GZ value. The shipyard carries out an inclining experiment to obtain accurately the vertical height of the center of gravity above the keel, Kg. A plumb line is suspended on the center line from a hatch combing and allowed to move over a horizontal batten in the lower hold when the known weight, W, is shifted a distance S. The length of the plumb line is L, and the distance that the plumb line is deflected is X. The GM is then subtracted from the KM calculated for the draft at the time of the experiment, and thus the light Kg is obtained. Once the Kg has been obtained, it can easily be adjusted in the usual way in case of any changes of weight on board. Lightship Kg is required by law to be provided on board along with a statement setting out clearly the items on board for that position of G. It is usually stated for the ship equipped and ready for sea with water in boilers, but no bunkers, fresh or feed water, stores, crew, and effects. For the experiment to be reliable, you will have to ensure that there is no wind. If there is wind, the ship should be head to wind. There is sufficient slack in the mooring and the ship is clear of the quay so that it can list freely. The draft and density forward, aft, and amidships are carefully noted so that W and Km can be accurately determined. The ship is upright at the beginning of the experiment. Only people directly concerned with the test should be on board. When the weights are shifted, the people on board should stand on the center line. The weights may be shifted using a derrick. The amount of weight shifted should result in the ship listing to about 4 degrees. There is no free surface of liquid in the ship. Boilers and tanks are either full or empty. Bilges are dry. There are no loose weights on board.